Wow. Okay. This one took a little bit to write. Alright, so Ted Kaczynski, right? Famous philosopher, we'll call him. At one point was a very accredited mathematician. He has a PhD, or had a PhD, in mathematics, and specifically he studied the subject of complex analysis, so the analysis of complex numbers and functions of complex numbers. And I thought, like 2 weeks ago or something like that, it would be pretty funny to look at his PhD thesis paper, right? I was wrong. It wasn't that fun. It took a pretty long time to write this video. It's a pretty complicated paper. But we're going to talk about it anyway because I'm not going to let all that work go to waste. Disclaimer, first of all, I'm an undergraduate computer science major, and this is graduate level mathematics that is no one's even talked about for like 40 years or whatever, Just know I tried my best here, guys. I'm like 80% confident in what I'm saying is correct, but like, take what I say with a grain of salt, alright? I tried my best here. Alright, so like, before we can even talk about what his paper is even trying to do here, there's a whole bunch of material that we need to like talk about and explain to even understand what Kaczynski's talking about here. So this is kind of the format we're going to go with. And you can probably kind of start to see why it's taking this video took me so long. Right. Oh yeah. I should probably start off by saying, alright, boundary functions. That was the title of his PhD thesis / dissertation, whatever. Boundary functions are very, very uninteresting. I'll come out and say that right now. Don't get your hopes up. It's not very exciting. They're actually the least interesting part of this paper, if I'm being honest. But that's besides the point. Anyway, first we need to start out by saying what are boundary functions, right? Then we need to talk about some set theory, some other stuff Kaczynski kind of defined in his paper. Well, he didn't talk about this. This was other people who did that. But this is a fundamental part of his paper, curvilinear convergence. We need to explain that. We need to go over a little bit of measure theory just to be safe here. And then we got to talk about something called Beret functions. I hope that's how you pronounce that word. I didn't check. So let's get right into it, I guess. Alright, boundary functions. What are they? Alright, we're gonna do a little bit interactive here. Get ready for this. This is professional. Alright. First, before I'll say anything, just to be clear, for the sake of simplicity, I've omitted certain details from his thesis. It doesn't obscure the details any. Well, it kind of does. The concepts are going to stay the same here. But just to make it shorter, more concise, and easier to understand, I've omitted some details here. So this isn't going to be exactly what's on the paper, but it doesn't matter. Okay, first of all, imagine we have some coordinate space. We'll call this a coordinate space A. So first, we're going to start out by drawing some curve. Now, before we draw the curve, we have to follow 3 rules for this curve. 1, it must be a finite curve, so it must have a start and an end. Number 2, it's got to be what we call a simple curve, which is a fancy way of saying it can't overlap itself. So no loops, overlapping, whatever. You get it? And number 3, its endpoint must be on the x-axis, right there. Alright, so knowing those 3 rules, we can just draw some arbitrary curve, bam. We'll call this curve gamma. Now, we're going to create a second coordinate space. We'll call this coordinate space B, and we want some function which can map points from coordinate space A to coordinate space B. So we'll call that function f. So for any point on coordinate space A that we plug into the function f, it will return a corresponding point on coordinate space B, right? Simple, function, right? It doesn't matter, it doesn't need to be defined. This is just the theory behind how it works. Now, for any curve that we draw on either of these two coordinate spaces, they can be thought of as sets of points. And as we travel down this curve, or travel along it from its start to its end point, it's going to approach this end point on the x-axis. So we can think of this point on the x-axis as the boundary or the limit of the curve. It's the farthest the curve can go. So what we're going to do is we're going to define another function, call it phi, which takes points from the x-axis and maps it onto B. And we want this function phi to have the certain property that as we travel along our curve on coordinate space A, so we're going from the start to the end point. We're plugging in the points. That is going to equal phi at our endpoint. So in other words, this function phi gives us the endpoint, the corresponding endpoint of this curve on coordinate space A, and it plots it on coordinate space B, right? So like if we call this point, alpha, this point here would be phi of alpha. And that's a boundary function, put simply. Very interesting stuff, I warned you. Alright, F sigma delta sets. Besides having a really funny name, it's actually a really bad name, because mathematicians like to give really stupid names to really simple concepts. So all this is that, say we take, some set, we take a bunch of these. It doesn't matter what are in these sets, but we're just going to write out a few. Right, so arbitrary sets full of arbitrary things. It can be, I think a qualification is that they must be finite. Anyway, we call a F sigma set, so just F sigma, is the union between any two or more of these sets. So if we take, P1 to equal the union of S1 and S2, right? This forms a F sigma set. Cool. And we can do the same thing here. Now, an F sigma delta set is the intersection between any two F sigma sets. So right there, F sigma delta set. It's not that complicated. You need to know a little bit of set notation, but alright, curvilinear convergence now. This is probably the most difficult to understand concept of this paper. It's the most abstract, kind of. Well, I mean, all of this is very, very abstract, but anyway, um, for all of these, I've been trying to phrase it in a way that's kind of more reasonable than how it's worded in the paper. For this concept, there really isn't any way to put it, better way to put it. It's just, yeah, the way it's described in the paper is honestly the best way to describe it. There is no better way to phrase this, but I'll try my best. Alright, same thing as before. We're going to draw out, some coordinate space, some curve on that coordinate space, and some function f. So the set of curvilinear, by the way, as a side note, this is an awful word. Who invented this word? Terrible. Anyway, set of curvilinear convergence is the set of all points on the x-axis such that for this particular curve and this particular function, there exists a boundary function. Doesn't make any sense. What's a better way of putting it? The best way, or maybe a more concise way of saying it, is that it is the largest set of points on the x-axis for which a boundary function can be defined for this arbitrary function f with this curve. Knowing the specifics of this isn't too important. You just have to know it exists, really, to understand the rest of the paper. So we'll just move on from it. Don't dwell on it too long. Alright, so now we need to make a quick note on measure theory. Specifically, we need to talk about what measure is so that we can understand what a measurable function is for one particular point. So we're just get through this real quick. So a measure is the sort of generalization of the notion of length into higher dimensions, right? If you have just some line, the start and an end, this line has a finite length, right? We can, use basic algebra to figure out how long this line is, right? This line has a measure, and the fact that this line can exist implies that this coordinate space is what we call a measurable space, right? So, in other words, for any 2 points, or for any, line or whatever that exists in the space, we can define some length for that line. And a measurable function is simply just any function which maps between two measurable spaces, right? So if this is a measurable space, and this is a measurable space, and this is a measurable function. Got it? Great. That's about all you need to know. For Beret functions, or Beret functions, probably how you say it, are actually the most interesting part of this paper, or the most useful, or besides measure theory, it's the most useful part. Actually, we talked about set theory, that's pretty useful. They're cool. Alright, so what are they? Okay. This is going to be a little weird analogy, but let's just hold out, okay? So imagine we have some machine, right? And this machine generates certain functions, right, based on a pattern. So it just pops out onto a conveyor belt or something, I don't know, a bunch of functions. And these functions follow some pattern, right? It's being generated by an algorithm. The technical term for this is that this is a sequence of functions. So the point of a sequence is that it follows some pattern. And what we say about sequences is, or what mathematicians like to study about sequences, is what happens when we go out to infinity. So we keep generating these functions according to some pattern. What happens if we just keep doing it over and over and over again? Does it eventually reach some final function, right? Do the changes between each one of these get smaller and smaller and smaller to the point where we approach some function? So again, the technical way of putting this is we say the limit of our sequence does it approach some function, new function g. It took me a little bit to remember how to write that. Anyway, so if it does approach something, we call this function g a class 1 Beret function. So it is the pointwise limit of a sequence of continuous functions. Right, so these are the continuous functions that our machine here is generating. They're also referred to as class 0 Beret functions. We can also say more generally that any class n Beret function is the pointwise limit of a class n minus 1 Beret function. Okay? A lot of this analogy was pretty bad, but it doesn't matter. The point here is Beret functions exist, and Ted Kaczynski wanted to know some certain things about the relationship between these guys and boundary functions. So that should be it. Now we can actually talk about the paper. Alright, so what did Ted Kaczynski's paper cover? What was he trying to do with, this 80-page paper monstrosity mess? So, in the first few pages of his paper, he lays out 4 distinct goals, things that he is trying to prove about boundary functions. So number 1, he wants to show that for any f sigma delta set, that set must be the set of curvilinear convergence for some arbitrary function. The reason this one's so significant is that other mathematicians had proven the inverse of this, that any set of curvilinear convergence must be a f sigma delta set, and Ted wanted to prove the opposite, right? He wanted to prove this. So the next thing is that if we have some boundary function, that boundary function must be of class 1, of Beret class 1, right? If it maps from the x-axis to some coordinate space, it must be of Beret class 1. And then he goes on to show this sort of property here more generally, right here, which is that for any Beret class n function, the corresponding boundary function for that function must be at least class n plus 1. Okay? And then finally, the last thing you wanted to show is that boundary functions do not necessarily need to be measurable functions. So they do not need to have some distinct sense of measure to it. And that's kind of the whole paper. I'm not going to go over the specifics of how he proves all of this. I'll reiterate, I'm an undergraduate computer science student. Most of this was already over my head. So actually taking the time to read the next 70 pages of his dissertation and figure out how exactly he accomplished all this It's probably not necessary. I'm pretty satisfied with this, and you probably should be too, unless you really want to know, in which case you probably need a PhD to understand any of it. Alright, so moral of the story here, what Ted Kaczynski did, the math he did, wasn't all that useful. We'll be honest here. And I'm not just saying that because I don't understand all of it. I'm saying that objectively. Like, a couple years after he published his dissertation, the entire field that Kaczynski studied, not all of complex analysis, but this one particular subfield regarding boundary functions and curvilinear convergence and whatever, people stopped caring about it. Everyone kind of figured out everything that there was to say about it, and people were just content with leaving it there, and no one's really cared about it since. That's not to say that what he did was useless. It just so happens that when you're working with math, this theoretical things come and go in fads. But what Ted Kaczynski did was a genuine contribution to the field of mathematics, and that's pretty impressive. Even if those contributions are things that no one cares about, it's still pretty impressive. So again, moral of the story here, don't let anyone tell you what to do. If you want to waste your life doing something that people are saying like, you shouldn't do that, that's pretty dumb, don't waste your time, don't listen to them. Do whatever you want with your life. Be happy, man. As long as you're not blowing up people, do whatever you want. This video took way too long to make. Hope you like it.